Welcome to my channel. So today's problem, we have this problem in calculus of variations. We have a certain city in which the rate, or actually we have the cost per unit length of building paths or roads is given by the function this. So here we need to understand first what this one is. The cost per unit length, meaning that u of xy would have a unit of currency per unit length. So, for example, in the Philippine setting, that would be PHP per unit length. So, it could be per meter or per kilometer. And where alpha and beta are known constants. So, the units of alpha here is clearly in PHP in currency per area, per unit area per meter squared, while beta is in currency. So, the units of alpha and the units of beta is different. Okay, these are known constants. So this is for x and y greater than 0. So we have a city that is just constrained in the first quadrant of the xy axis. So let's understand this first. We have, this is the city, okay, the positive x and the positive y. And if you build a road, so let's draw that road from one point to another. Okay, so let's now understand this. Now, the cost of the path is actually dependent on not only the distance, the length of the of that path or road, but also where particularly the road is built, because we have a different rate. Just like, for example, building roads or building structures in the city proper would be much more expensive than building it in the more rural areas. So, for example, this road here would have a certain cost, and that would be equal to the just the length of the road, the total length of that times the density function. By the way, we can actually understand this as a density, a linear cost density function. Linear means it pertains to the length. So depending on the type of road, the cost will be different. For example, if we have another type of path, let's use orange for that one. This path here, for example, would have a different cost, or we can have a straight path, that one in yellow, it would have a different cost, or even a path like this, that one, or another path would be um, this one right there. So each of these will have a different cost. Okay, so clearly here we are asked to find the cost of a straight path, but before finding the cost of the straight path, let's understand this, the cost function. It's not just an ordinary function, but actually a functional in which it changes its value as the function changes. So here, the cost function C is just equal to is just equal to the density, the cost density function, the linear density function U times the total length of the curve or the road being built. So we can think of this as U times the total length of the road, or we just call this that as D. So how do we find now the distance D? Okay, given a curve, what is now the total distance D? Well, we can actually do that by um, taking a sample, a small portion of that path. Let's say, for example, this one here, that one. Okay, that one in black. And that one in black, let's call that DS. And that DS, it's approximately a straight line, will have a vertical distance of dx, and I mean horizontal distance of dx and vertical distance of dy. So based on the Euclidean metric, you're assuming a Euclidean space here, that would be ds squared equals dx squared plus dy squared. This is actually the Euclidean metric. Okay, so that the cost function is just would be just be given by, let's call this c now, will be a function of x, of the point, specific point, and y. And not only that, it will also be a function of the first derivative of y, because as we can see here, the derivative of y will come out. Okay, so from here we can see that ds is just equal to the square root of dx squared plus dy squared. That is now the length of this small infinitesimal part of the curve. Or this is just removing dx out of the square root. We get now 1 plus, we have here dy over dx squared, but this is just y prime. So hence, our cost function would just be equal to u of xy. So alpha x plus beta over y times this distance. Let's call this dc, because this is an infinitesimal cost. The cost of that infinitesimal distance, small length of the curve. So we have now, this is equal to the square root of 1 plus y prime squared dx, where y prime is just dy over dx. Now, since we are asked to find the straight path from a certain point to another point, okay? So meaning that here, since we have a straight path, meaning that y is equal to sum ax plus b, okay? Y is equal to ax plus b. This is a linear function. So we can now replace y by this, and we see that our uh, integral, our cost functional would be, this is a functional because it's a function of functions, would be the integral from point 1, let's call that the initial point, x naught, to some x of alpha x plus y is ax plus b. So this is now beta over ax plus b. And then, now what is y prime? From here, y prime is equal to a. So this now becomes square root of 1 plus a squared dx. So let's just denote this as k. Uh, well, we can just, okay, so this is now easy to integrate. We can actually separate the integral into two. So this is just equal to um, square root of 1 plus a squared um, times the integral of x naught to x of, since alpha is constant, so alpha x dx plus we have beta over ax plus b, the integral from x naught to x of, we have, sorry, this is beta here, and then dx over ax plus b. Okay, let's delete that. Now this is very easy to integrate, while this one would take would actually um, take us would take simple substitution. We let we can let q equals ax plus b, so that dq is equal to a dx, so that dx is just dq over a. So here our integral now, this is 1 plus a squared times, this integral is just x squared over 2, so this would be um, a x squared, a over 2. Okay, let's write it here, square root of 1 plus a squared times alpha over 2 times x squared minus x naught squared. Sorry, squared is here. Plus, we have beta over a. This becomes integral of du over dq over q, in which the integral that would be ln of u. So ln of ax plus b evaluated from x naught to x. So that would give us ln of ax plus b minus ln of ax naught plus b, or we can just take this as ln of some ax plus b, okay, over ax naught plus b. Here is x is no longer the same. X is no longer a variable. It's actually just a constant. The final, okay, final point, final x. Okay, by the way, we are evaluating from x naught, y naught to some distance x, y. Okay, some point x, y. Okay, so this will now be the our cost. Okay, okay, so we're done with number one. We can actually have we can actually solve also a follow-up question. What would be the cost if we are building a parabolic path from one point to another, from the point x naught, y naught to some x, y? Well, that would just be, again, for the parabola, let's just assume a parabola, okay, y is equal to some ax squared plus bx plus c, so that y prime would be equal to 2ax plus b. So our cost function for this road here is equal to the integral from x naught to x of uh, alpha x plus beta over ax squared plus bx plus c times, okay, the square root of 1 plus 2ax plus b squared dx. Now, this is actually quite difficult to integrate. So, we'll not proceed with this one. Okay, but if you can integrate this, then you will get exactly the cost of building a parabolic path from point A to point B. Of course, this parabola must pass through x naught and x. Okay, otherwise, it doesn't make sense to evaluate this one. Okay, let's go to number two, the second uh, part. Derive the differential equation. Now, this is actually easy. Notice that this is our integral. Okay, I'll write it here. The cost functional x, y, and y prime would be equal to the integral from p1 to p2 of alpha x plus beta over y square root of 1 plus y prime squared dx. Now, clearly, we can take this as our Lagrangian. Okay? This whole thing here is our Lagrangian L. And we can just calculate this. We can we can just calculate the Euler-Lagrange equation by first take partial L over partial y, and that would be, when you take partial L over partial y, you have, this is the only term that has y, so beta negative beta over y squared times square root. So that would be, yeah, that would be negative beta over y squared times square root of 1 plus y prime squared. Okay, how about partial L over partial y prime? That would give us, okay, both of these has y prime. So you have now alpha x plus beta y, and then times, okay, this is raised to 1/2, so negative, raised to 1/2, so this is 1/2, and then, okay, this would be y 2y prime over 2 times square root of 1 plus y prime squared. So this just simplifies to, so this is beta. So alpha x plus beta over y times y prime over the square root of 1 plus y prime squared. Now, we're ready to find the Euler-Lagrange equation. Okay, we'll use this form of the Euler-Lagrange equation, d over dx of partial L over partial y prime minus partial L over partial y equals 0. So, I will no longer evaluate this d over dx. You have to take d over dx of this one, but it's kind of messy. You have to differentiate three variables here, x, y, and y prime in terms of x. I'll just write it in the concise form. Anyway, we will not be evaluating this is this different. We will not be finding the solution for this differential equation because it would be too complicated. It's actually a nonlinear differential equation. So we have this d over dx of alpha x plus beta over y times uh, y prime over square root of 1 plus y prime squared minus, so it becomes a plus beta over y squared square root of 1 plus y prime squared equals 0. When you solve this, you get now the solution to this is it will give you y of x. Okay, when you solve this equation, you will have the y of x, which is the algebraic equation of the path from a to from any point, from one point to another point. It's an algebraic form, it's a closed form. So yeah, you will have that one. Now, if you think I made some algebraic mistake, because I usually make mistakes, I solved this problem on the spot. So I didn't solve this before making this video. So I might be committing some algebraic mistakes, or yeah, some sign. So feel free to comment in the comment section. Feel free to write your correction in the comment section. Okay, I will not be mad at you. I will be thankful because um, yeah, I'll be thankful for correcting me. Okay, I think this is correct now. Okay, thank you for watching, and if you have not subscribed yet, please subscribe because we will have more problems to solve in this channel.